Let's start by reviewing some of the different symmetries. I'll show you several geometries, most of which appeared in the notes for reading assignment 5. And for all those symmetries, I'm going to discuss what kind of symmetry is present, and I'll sketch the field and also show you what a good choice of Empyrean contour is for applying Stokes' theorem. Now let me remind you that Stokes' theorem looks like this. You have your contour integral of a vector field is equal to the flux of the curl of the vector field F through the surface S, where the surface S needs to have the same orientation as the contour by the right-hand rule. So your fingers would align with the contour and your thumb should align with the normal vector to the surface. Now in most of the problems, actually in all of the problems for this topic, you will be given this J, or you'll be asked to find J, for example, which is the curl of the vector field F. So your problem setup would look like the governing equation would look like this. This would be the right-hand side and this would be the left-hand side. Okay, let's discuss the geometries. For this case, this is a slab. Your vector field would look something like this. So all of those currents would produce the field that would go based on the right-hand rule. You would imagine aligning your thumb to the current and your fingers would curl around this current density, producing the field like this. On a trace, this would look like this. Your F would go in the negative y direction here and positive y direction here. And then inside the contour also something similar will happen, right? Okay, so a good contour for this case is a contour that will capture J, so it would have a normal vector that's parallel to the direction of the current density. And also, another feature of a good Empyrean contour is that the contour aligns with the field on some of its portions and is perpendicular to the field on the other portions. This makes everything much easier to integrate. The kind of symmetry that's present in this problem is planar symmetry, and it's discussed in section 4.1. The next kind of symmetry is, well, geometry is like this. You have a cylinder. You see the way I drew the current. This is not a shell. This is a cylinder with some sort of volume current density, current flux density. The field produced would go around this cylinder like this. Again, by the right-hand rule, your fingers would align with the field and your thumb would align with the current. And then here it would look something like this. A good Empyrean contour is, again, the one that captures the current density. So it would be a circle in this case. In this case, the symmetry is cylindrical because nothing depends on theta and nothing depends on z. And the only sort of important variable in this case is the distance from the z-axis. And the kind of current that we have here is the axial current flux density. There is another option. The reason why I'm specifying the kind of current density is because in a cylinder, you could also have a situation like this, where the current is flowing circumferentially. Okay. So, and this is discussed in section 4.2. In section 4.3, you have geometries like this one. This is an infinite axial helix. This infinite helix. The kind of current density you have is circumferential current flux density because it goes sort of around the circumference instead of going like it did in this problem. The field produced would be like this. The field produced, you could imagine aligning your thumb to the current density, and as a result, your field would go like this. Now, I want to mention there will not be any field outside of this helix. We had a discussion in tutorial 8 about why this is the case and why it's a very good assumption to have this. Here, this is how this looks like. This is the field. Field outside is 0. And the contour you would set up would again capture your current density. You could set it up in either counterclockwise direction on this trace or clockwise direction on this trace. It doesn't really matter as long as you're consistent and very careful. Yes. And this is discussed in section 4.3. Also in section 4.3, there is a bit of discussion about other kinds of cylindrical geometries where the current is circumferential. One of those would be when instead of this helical kind of geometry, you just have a sheet of current. That's another possibility. You could also have, which I'm not showing here, you could also have shell with current that's not thin. So you would have some sort of thickness to the shell. And then instead of surface current, you would have a volume current density that's distributed over some volume. But that's not what I'm showing here. Here I'm just showing a shell. In a shell, the current would look very similar to the infinite helix. Sorry, I meant the field would look very similar to the infinite helix. And the contour you set up would also be the same. Now, two things I want to emphasize. First, how I got the direction, again, by the right-hand rule. You see this current goes out of the page. And if you imagine aligning your thumb to the current, your fingers would align with the field. That's one thing. Second thing is that actually the fact that I said this and this are very similar, this is kind of an approximation, right? Because in this case, this is really a sheet of current. In this case, we're pretending that our field looks like it's a sheet of current and that it doesn't see those individual wires, right? And this is what we discussed a bit in tutorial 8. In section 4.4, there is a discussion about toroidal helices. Those are similar to axial helices, but they're instead wound on a toroidal form. So you would imagine this donut-shaped object, and then there is a wire that's wrapped around it, and there is a current, wrong pen, color, there you go, current that is passing through this wire. The trace would look like this. Here you see coming out of the page are these wires because they are on the inner circle, because on the inner circle J is coming out of the page. Then on the opposite side, the wires are going into the page. The field produced by the torus will be somewhat similar to the field produced by the helix. So it also goes sort of inside the helix. And is 0 outside the helix. The way I got this direction, again, is by the right-hand rule. Your thumb would be aligned with the wires, and the rest of your fingers will be aligned with the field. So this is the field F, and outside it's 0. Now, the contour that you would select for this problem is going to be the one that captures the current nicely. So the normal vector to the corresponding surface would be in the same direction, or would be aligned with the current. You could make it same direction or opposite direction, but you just want to make sure that you're capturing the currents. So this would be your contour, for example, in this direction. You also want your contour to be aligned with the field, right? And this is the normal vector I was talking about. In the same section, there is a discussion about circumferential sheet current flux density that's going around a torus. So it's exactly the same kind of situation. The only difference is that instead of having a helix with wires, you have you would have a surface current that's going on this shell like this. The cross-sectional, the trace would look very similar. I just drew these circles here to sort of show that it's a shell instead of individual wires. But really, I could have just copy-pasted the same image because there is really not much difference. The field is also going to be in the same direction, and you would want to choose the same contours. So the field is going like this. Outside is 0. And your contours would be circles that have a surface that captures the current. So circles that go inside of this shell. Here I'm showing a dotted line because it's inside of the shell, so you can't see it technically. You could also have a situation where where your problem is not symmetric, but it's made up of symmetric objects. For example, this problem, one of the objects you have has this kind of current density, so it's axial current density. Actually, let me draw it with colors so that you can see which field is produced by what. Maybe I'll choose brown for this guy. So this is the current. And the field produced is in this direction. Another object you have has circumferential current density. So that's a totally different story, because you can't reuse the same kind of contours for different types of objects, right? For different types of symmetries. So this one has this kind of J, and the field produced is going to be like this. So this would be F1. And the brown one is F2. In tutorial 8, there was quite a lot of discussion about superposition, so you can go back and check what that was all about. And let me show you, in case you're not convinced the contours should be different. You see, this is the contour for circumferential current density. And for the axial current density, this is the kind of contour. Because you want to make sure that your current actually passes through your contour. Otherwise, you're just not going to enclose any current, and your Stokes theorem application would just not give you the right conclusions. Like, it just would be inconclusive, if anything, or you might make a mistake. Now let's do problem 5 from section 4.6 in assignment 5. The problem involves two different objects. One is an infinitely long cylindrical sheet with current density shown, oh no, what am I doing? Shown here like this. It's going in the circumferential direction. It goes counterclockwise when you look at the xy plane. That's why this the direction is in the theta hat direction. The magnitude of the current flux density is given by J(S0), so some constant, times delta of R minus R1, where R1 is the radius of this sheet, and it's measured in amps per meter squared. So this guy is current flux density. And it's the one shown here. The second object is a cylindrical annulus. It has inner radius of R2. R2 right here. Outer radius of R3. It has direction that's circumferential as well, but it goes in a clockwise direction when you look at the xy plane. So it's the one that's shown here. And you can see there is negative theta hat direction to it. The magnitude of this current flux density is given here. It's J1 times R, where R is the distance from the z-axis, and it's measured in amps per meter squared. Now, this current flux density is like this between inner and outer radii of the annulus, and at all other values of R, it's going to be 0. The question tells you that the total field produced by these two objects is equal to 0 at the point 0, 0, 0. So the total field right here is equal to 0. And it asks you for two things. RZ trace, which you should draw even if the question doesn't ask it, and the constant J1 in terms of R2, R3, and J(S0). Now, there is two ways to do this problem. One is using superposition, which is what the reading assignment does. And another is using is just by directly solving it. So we have two ways. Superposition, and direct solution. To solve this problem using superposition, you would first break the problem into two. You would first pretend that the only thing existing in the universe is this annulus, for example, or maybe the sheet. Let's start with the sheet. So you would formulate the problem imagining that sheet is the only object, and then you would set up your Empyrean contour. You would apply the Stokes theorem, so you would evaluate the left-hand side, the right-hand side, and you would equate the two. And this will allow you to solve for the field from the sheet in terms of a whole bunch of other things, right? Then the next thing you'll do is you will do the exact same thing for the annulus. So you would set up another contour. You would simplify the left-hand side, the right-hand side of the Stokes theorem, and you would equate the two. And then you would solve for the field from the annulus. Then you would add the two together. And then you would set it to 0 at the origin and then solve for everything you need to solve. So this is using superposition. Superposition works no matter what kind of objects these are, as long as each individual object has a symmetry, you're good. Now, in this case, actually, these two objects have the same kind of symmetry. So the overall problem has a symmetry because the current is going in a circumferential direction for both of these objects. It's producing the field that's in the z direction for both of these objects. And also both the current flux density magnitude and the field magnitude is only dependent on the distance from the z-axis. So the fact that these two objects have the same kind of symmetry lets you just directly set up the Empyrean contour. So you would set up only one contour for this guy. And then evaluate the left-hand side, the right-hand side, and equate the two. And then solve for what you need to solve. And then you would, I guess, you could solve for the field in terms of everything else or for something else. But the main thing is that you just solve it using one contour. So maybe I could say, solve for unknowns. So here, two different contours, completely separate problems that you join together at the very end when you're solving for unknowns. Here, just one contour and everything goes in one sort of step. But this, you need to be very careful. So you need to always know whether you can apply it or not. So if there is two objects, be careful whether you actually can use direct solution. Let's first solve the problem using superposition. So this approach, and as I'm doing that, I'm also going to show you how to sketch the RZ trace and what it means. The first step for superposition approach is to find the field from the sheet. So this is this purple object. The RZ trace for the entire problem looks like this. You see the sheet current is going into the page. Now, what is RZ trace? A lot of students actually ask this. So RZ trace is a trace where one of the axes is the distance from the z-axis and the other one is z. The reason why you don't have to specify whether it's yz or it's xz or it's some combination of the two is because no matter which theta we take the slice at, we will get the exact same picture. So this is how it looks, and then the sheet current looks like this. It's going into the page. Because you see, if you imagine taking any slice, the sheet current is going to go into the page. So you see, if this was R, this was Z, well, this was Z, then the sheet current is into the page. I'm actually going to erase this because it's too crowded. Okay. So for this part of the problem, we are pretending that the only object right now is the sheet. So this purple here, so this is J sheet. The sheet produces the field like this. It's going in the positive Z direction inside of the sheet, and it's equal to 0 outside of the sheet. What else we know about the field is this. We also know that, so it's in the Z direction only. Well, in this case, it's 0, but it could think it's in the Z direction. So it's in the Z direction and it has some Z component. The Z component depends only on the distance from the Z axis. So it doesn't change when we go, for example, up. We see the exact same picture, the same field. The same thing happens when you change theta. So you travel this way, you will see the exact same field. Okay, the next step is to set up an Amperian contour. The way we would set up the Amperian contour in this case is to capture the current density. Let's make n hat in the negative theta hat direction. We could make it theta hat as well. But in this case, it's in the negative theta hat, so it's out of the page on the RZ trace. The left side, so R1, for the contour is going to be at R equals 0. The reason why is because the point where everything is, the question is talking about is the origin, right? So we wanted to pass through the origin. The orientation of the contour, sorry, this is n hat, so the orientation is this way. Okay, so R2 is going to be outside of this, where the sheet ends. So R2 is greater than R1, where R1 is the radius of the sheet. And then Z coordinates could be arbitrary for the heights of these two sides. Now let's evaluate the left-hand side of the Stokes theorem. This is the contour integral shown here. It's made up of 4 parts corresponding to each side of this contour. So this is CZ1, CZ2, CR1, and then this is CR2. So I broke the integral into these 4 parts. I'm actually in the corrected notes, you have this closed contour sign here. So then not all of these integrals are non-zero, right? We have, for example, we have this side where the field is 0, right? We just discussed how this field is 0 outside of the sheet, and this contour, part of the contour, passes through this region. This means that for this integral, this f is actually equal to 0. For this one, it's actually interesting because we have CZ1 has this ds going in this direction to the right. But f is going either, where did we find out? Either up or is just 0, right? So either the two vectors are perpendicular, so ds is perpendicular to the field, or the field is just 0. In either case, this dot product is 0, so the entire integral is 0. Same thing for this guy. So then, because this also has ds going to the left, and the field is either up or equals to 0. So this integral is 0, same for this one, and same for this one. So we're left with just this guy. Next thing I did is I plugged in f from the sheet, but not just anything, but the expression on this contour. So I used this expression, I plugged it in. But not just that, I also used the fact that on CR1, which is this contour, the value of this r is not just arbitrary, it's equal to r1, which happens to be 0. This is what I wrote here. Then the next thing I did is I realized that z hat dotted with ds is equal to negative ds, where ds is the differential length element. The reason why is because for this contour, ds is down, but z hat is up, right? So then when I take a dot product, the result is going to be magnitude of z hat times the magnitude of ds, so differential length element, times the cosine of the angle between the two, and this cosine is equal to -1. That's why I get negative ds. So this negative comes out of the integral, and then I'm left with just this guy. Next thing I did is I took this and I shifted it out of the integral. Now it's really important why we are allowed to do this, and the reason why is because anywhere on CR1, this quantity is constant, because r equals 0 is just a constant, right? And we're changing, no matter where we are, r just stays 0. So this guy comes out. So we have this. And then we're left with this integral here, which just means the length of the portion of the contour, right? Which is delta z. Remember, delta z was the height of the Empyrean contour. So that's it for the left-hand side. Now let's talk about the right-hand side. On the right-hand side, we have this flux integral, flux of the current density. You see the current density is going into the page, right? And the vector ds, we determined that we wanted to go in the negative theta hat direction, and we know that this is out of the page. So we know that J, actually let me write it here. We know that J sheet dotted with ds, where ds is the differential surface element, is equal to, we have the two vectors going in the opposite direction, so we have negative magnitude of J of the sheet times magnitude of ds. That's how I got this guy. Here, what I did is I plugged in the expression for the magnitude of J sheet, which was JS0 delta R minus R1. You can check on the previous page. I did that, and then I set up the integral. Our integration is going to be over R and over Z. The reason why is because the contour extends in R direction and in Z direction. The bounds are going to be from Z1 to Z2. The bounds on R are from R1, which is 0, to R2. Remember, R2 was greater than R1. Now, really important, a lot of people put a Jacobian here, but actually in this case the Jacobian is just 1. We shouldn't be putting anything here. The reason why is because of this. So what I think people are thinking when they're putting Jacobian is they are thinking of dr d theta. When you're differentiating with respect to r and theta, what you have is, let's say, some sort of, I'm thinking arbitrary problem where just you have something like this and you're integrating over r and over theta. So your surface elements look like this, where this guy is dr and this guy is r d theta. And this is exactly the Jacobian. So your differential surface elements, you can't take them as d theta times dr. For one thing, because d theta has no units and length of this guy should have units of length. And also because d theta is not the length of this guy. R d theta is the length of this guy. That's why when you're integrating dr d theta, you need the Jacobian. And Jacobian is not just 1. Now, if you're integrating like this over r and z, you see how your differential surface elements are just dz times dr. You don't need any scaling factor. You don't need any Jacobian. Now, if you want more details about why you don't need Jacobian for this guy and you need it here, you can either try parameterizing the two kind of surfaces, or you could ask your TA at office hours. Okay, so this is this integral. Now let's actually evaluate it. Integration over z is going to give us delta z. This is what I put here. Js naught comes out of the integral. This is what I put here. And what I'm left with is this integration of the delta function over dr. This interval of integration captures the peak of the delta function, which happens at r1. That's why, by the way, I specified that r2 is greater than r1. So then this integral is equal to 1. And we're left with this guy. The next step is to equate the left-hand side and right-hand side. The left-hand side we already solved for. It's right here. The right-hand side is here. This is just a copy of these two things. Then we are ready to solve for the field at the origin. So you see, origin means that our r equals to 0, right? So when we rewrite this expression for f, this one, this is f at r, but this guy has r equals 0, and then z hat. So we can plug in what we get from here. This line will give us f at r equals 0 equals to, negatives cancel, delta z cancels, and then we're left with js0. So this is equal to js0 times z hat. The next step would be to solve for the field from the annulus. So let's do that. So here I already highlighted the current density associated with the annulus, and the magnitude of this current density is J1 times R. The field produced by the annulus is going to be 0 outside of this annulus, and then inside the field is going to be, again by the right-hand rule, it's going to point down. And then within the body of this annulus, it's probably going to be something like this. We don't exactly know how it's going to go here. But the main thing I want to show you is that it's in the negative z hat direction, or it's 0. So we could write it like this. So it has z hat direction. Well, in this case, we know it's negative, but we could put this negative inside of this scalar quantity. And we also know that the z component is going to be a function of r only, so only the distance from the z-axis. So similar to the way it was for the sheet. The Empyrean contour is going to be like this. We're interested in the field at this point, right? So this means that we want, again, our contour to pass through this point. And we would make the contour capture the entire current density. So let's make the contour go all the way until R2 greater than R3, where, remember, R3 is this outer radius of the annulus. So this is the contour. Let's orient it this way. This corresponds to n hat going like this. This is equal to negative theta hat. Because remember, theta hat goes into the page. And this is the opposite direction. Okay, so again, the dimensions of the contour are delta r by delta z. The size will go from r equals 0 to r equals R2, it doesn't matter what R2 is as long as it's greater than R3. So that this side passes outside of the annulus, and the z coordinates are arbitrary. This way, the left-hand side of the Stokes theorem is going to be again broken down into 4 pieces. Here again, again we have zero field outside of the annulus. This is on this side. Here, the differential length element is perpendicular to the field. So we're only left with this integral. Again, plugging in the expression for this vector field on this contour. We plug this in, and we also use the fact that on the contour, on this contour, r is equal to 0. Then the thing I do next is this. I use the fact that my ds on this contour is downwards, and z hat is upwards, so they're in the opposite direction. So the dot product is going to be equal to negative ds. So then this negative comes out of the integral. This guy is again a constant because it's some function, but it's already evaluated at r equals 0, right? So it's just a constant. So we have this, and this is again delta z. So this is how I got this. For the right-hand side of the Stokes theorem, we have again the integral of the current flux density. So then this total flux is equal to this. The way I got this is as follows. We have our current density going out of the page, right? So we have, when we evaluate this dot product, we have magnitude of J annulus, magnitude of ds, times the cosine of the angle between the two vectors. But we know that ds is out of the page, so is this j, right? So then this is going to be with a positive sign. That's how I got this. Next is to actually integrate. So we have, again, dr dz. This is the magnitude of this j. Bounds on z are the bounds of the contour. So from z1 to z2. Now, the bounds on r, it's very tempting to say 0 to r2, but this is not correct to do that because you see we're integrating a non-zero quantity. But the current density is non-zero only between this point and this point. So between R2 and R3. So we should put R2 here and R3 here. Then this J1 comes out of the integral because it's a constant. Integration over z is going to give us delta z. Then we're left with the integral over r only. And then we have J1 delta z. This guy integrated gives us r squared over 2. And plugging in the bounds, we're going to get this. So this would be the right-hand side. The next step is to equate the two sides and solve for unknowns. The right-hand side, sorry, the left-hand side was this. This is what I wrote here. The right-hand side, I copied it here. From this, we get that F annulus at r equals 0. So the z component of F annulus at r equals 0 is equal to, after we cancel this, is going to be negative J1 R3 squared minus R2 squared over 2. Then, using this, we can get the field at 0, 0, 0, where we're interested in. So we use, again, this formula for our field. We know that at 0, 0, 0, r, which is the distance from the z-axis, is equal to 0. That's why I wrote this. And this we already solved for right here. So plugging it in, we get J1 R3 squared minus R2 squared over 2. So this is the field from the annulus. And we already found the field from the sheet. On the next page, I copied the two fields and added them together. Let me show you what I got. So we have the total field. This is not just anywhere. This is at 0, 0, 0. Actually, let me use blue so I'm consistent in terms of colors. At 0, 0, 0, the field is the field from the sheet plus the field from the annulus, which is equal to this guy we found in the first part. And this is what I just shown you. And we know we were given in the question that this is equal to 0. Then factoring out this z hat and setting it to 0, we know that the only way for this to be the case is if this guy is 0. So we would set this to 0, transfer j as naught to the right-hand side. This is how I got this. Then the next thing I did is I multiplied by 2, got this here, and divided by this guy, which gave me j1 in terms of the variables that we were actually asked for. So this is it. This solves this problem. The next thing I want to show you is how to do this same problem, but directly, without using superposition. So to solve this problem directly, we can do the following. So again, we assume that the field is in the z-hat direction, and it's only dependent on the distance from the z-axis. Now, this is why, by the way, we can solve this problem directly. So I'm actually going to, everywhere where we use the symmetry of the problem, point out why in this particular problem it's okay to solve directly, even though there is two objects. So you see, the fact that there is two objects didn't break this property. So this is still the case because, well, it's just, we just know that both of these objects produced field that's in the z-hat direction or negative z-hat direction or 0. And both of these fields depend only on the distance from the z-axis. That's why the total field will have the same property. The Empyrean contour, we can choose the same kind of contour we chose before. Again, it would pass through this point. Let's make the direction the same. So n hat would still point in the negative theta hat direction. And let's make our R2 greater than R3. The reason why is because I don't want to place this side in a location where I don't know the field. I want to place it where I know it, right? Because then everything becomes much simpler. So if I place this guy outside, then I get to just cancel this integral for this side, right? But if I placed it, let's say, inside of this, the body of this annulus, things would get more complicated, right? Okay, so we have this contour. Again, applying Stokes' theorem, finding left-hand side of the Stokes' theorem, we get 4 contours, and then these 2 contours will give us 0. This gives us 0. And actually, well, this guy gives us 0 as well, because we chose R2 greater than R3. So we're left with just this guy. This is what I wrote here. Here I plugged in this expression for the field, and I also plugged in R equals 0 because this is what's happening on this contour. This is this guy, CR1. Now, we actually know what this guy is because we know that when we're at 0, 0, 0, f equal to f of 0, r equals 0, z hat, equals to 0. This means that f at 0 is equal to 0, right? So then plugging this into here, what you'll get is just 0 because you're integrating a 0 quantity. Then on the right-hand side, we have an integral of the total current density, the one coming from the sheet and from the annulus. We can break it up into 2 flux integrals here. For this integral, we know that J of the sheet is into the page, and the differential surface element is out of the page. So when you take a dot product, you would get negative product of the magnitudes, right? So negative magnitude J sheet times ds. Here, we would get positive. Why? Because this current density is out of the page. So then when you take a dot product with the differential surface element, you would get positive product. By the way, I keep pointing to this one. Well, the correct one would actually be another vector because n hat is not equal to ds, but they are in the same direction. Okay. So this is equal to plus JAN ds. Then this is what I wrote here. Here I'll have a minus, here I'll have a plus. Then on the next line, I wrote the actual integration. In both cases, we have integral over dr dz, dr dz. These are the expressions for the current density magnitudes. And then the bounds for z are the same. The bounds for r, well, here are the bounds that you would expect, from 0 to R2. So the entire area of this contour, of this surface, this is okay to do for the sheet because the delta function will already take care of the fact that of the fact that the current density is 0 everywhere except these points. But this is not the case when you're plugging in J1R. When you're plugging in J1R, you are not taking care of the fact that current density is non-zero only between these two values. That's why you have to take care of it separately by making the bounds correct. So then, okay, so I did that, and then I integrated, and I'm skipping the steps because the integration I already did it. It's exactly the same as in previous steps, and this is the result. You can check previous pages for how I got this. But what I did next is I equated left-hand side and right-hand side of the Stokes theorem. Left-hand side was 0. Right-hand side is this expression here. That's why I have this equality. And remember, we're solving for J1, so then I shifted this guy, well, to the left-hand side, and I swapped left-hand side and right-hand side. Then I solved for J1 by canceling this, multiplying by 2, and dividing by this. So you see the answer is exactly the same as before. So we've done everything correctly.